Welcome to lecture series on advanced linear algebra. Today we are going to talk about a topic is called linear functionals and adjoints. In this topic we are going to say if a vector space which is also equipped with an inner product, then we want to show for each linear functionals defined on the finite dimensional inner product space, there exists a fixed element in V where the linear functional is inner product of that fixed vector beta. And using these results, we will show suppose a T is a linear operator defined on the inner product space V, which is also finite dimensionals. We will show there exists adjoint of the T, which is another operator on the V, which satisfied certain conditions like for any alpha beta belongs to V, inner product of T alpha comma beta will be equal to inner product of alpha comma T star beta. And next will be what will be the matrix representations of the operator T and T stars with respect to an order basis, which is also orthogonal order basis for the vector space V. So, under this section we are going to answer these three important topics please. So, let me first show that for a finite dimensional inner product space, if we consider any linear functional on it, that this linear functional is basically inner product of some fixed vector in the vector space V. So, before answering this, let me consider a finite dimensional inner product space V over the field say capital F. So, this field is maybe real number or field may be complex number. For any beta belongs to V, consider a function f beta which is defined from basically from V to capital F, and such that f beta of alpha equal to inner product of alpha beta. Now, if I define a function from V to F like f beta of alpha equal to inner product of alpha beta, then we can easily show that this f beta is a linear functional, So, this can be checked quickly for any gamma and alpha belongs to V and C belongs to capital F. We have a beta of C alpha plus gamma is equal to, according to star, it will be equal to inner product of C alpha plus gamma comma beta. So, from the definition of the inner product, this is equal to C inner product of alpha beta plus inner product of gamma beta, and this is equal to C of f beta alpha plus f beta gamma. So, this implies f beta is a linear functional. Now, using this, let me introduce one nice results in terms of theorems. It is like this. Let V be a finite dimensional inner product space. Inner product space over the field is F. Let F be a linear functional on V. Then there exists a unique vector beta belongs to V such that f of alpha equal to inner product of alpha beta for all alpha belongs to V. So, I will prove that over a finite dimensional inner product space, any linear functionals is basically inner product of some fixed vectors in the vector space. I have to first find out the what is the element beta when a linear functional f is given to us. Consider a vector beta equal to a sigma of f of alpha j and alpha j, this one j equal to 1 to n, where b equal to alpha 1, alpha 2, alpha n is an orthonormal basis for V. So, for a given orthonormal basis, one can I will define a vector beta for a given functionals f like this. And the question is how to think that for a given orthonormal basis or given linear functionals, one has to consider the element beta equal to like star, or what is the geometrical interpretation of beta. All this we are going to answer shortly, please. But I can define a vector beta in terms of like this when as an orthogonal order basis if I consider B is given to us. Suppose if I choose like this, then I can define a vector like star. So, under this, so we can have a linear functionals a beta as a beta of alpha equal to inner product of alpha beta. So, I can define like this. We have a beta operating on alpha k. For each k, I am getting a beta of alpha k equal to inner product of alpha k and beta. So, this is equal to inner product of alpha k sigma f of alpha j bar and alpha j, j equal to 1 to n for any k belongs to I can say 1 to n. So, I have like this. So, this implies the linear functional we have defined a beta for typical beta, a beta of alpha k equal to simply alpha k and f of alpha k bar alpha k, where all other will be cancelled out because alpha 1, alpha 2, alpha n, this is basically orthonormal basis for the vector space V. So, therefore, inner product of alpha I and alpha j will be equal to 0 if I not equal to j. So, based on this I have a beta of alpha k will be equal to this, which is equal to f of alpha k. into inner product of alpha k which is equal to 1. So, this implies for each alpha k a beta of alpha k equal to f of alpha k. So, this implies a beta equal to f. So, we see for a given linear functional f, there exists a vector beta in V such that f equal to f beta. I mean to say f of alpha is equal to inner product of alpha and beta, please. Now, claim it is unique. It is unique. Suppose not. Suppose not. So, there exists say gamma which is not equal to beta belongs to V such that f of alpha equal to inner product of alpha gamma. Now, f of alpha also equal to inner product of alpha beta. So, 1 or 2 implies inner product of alpha gamma equal to inner product of alpha beta. So, this implies inner product of alpha and gamma minus beta equal to 0 for all alpha belongs to V. So, this implies in particular when alpha is equal to gamma minus beta, in that case we also have gamma minus beta and gamma minus beta equal to 0. Now, this is possible only for, so this implies there exists unique vector beta in capital V such that f of alpha equal to inner product of alpha beta. Now, the question is how to think that one has to consider beta equal to as sigma f of alpha j bar alpha j. How to know beta has to be of the form sigma f of alpha j bar and alpha j equal to 1 to n. For a given linear functional f, there exists a vector beta in V such that f of alpha is equal to inner product of alpha beta for all alpha belongs to V. Let alpha and beta belongs to V and alpha is equal to, let me consider with respect to orthogonal basis as x I alpha I equal to 1 to n and beta equal to sigma say y j alpha j equal to 1 to n. So, this implies inner product of alpha beta, this will be called to inner product of sigma x I alpha I and sigma y j alpha j equal to 1 to n, I equal to 1 to n, please n. Now, using the definition and property of the orthogonal basis, we will have this is equal to, I can straightway write down this is equal to sigma x I and y I bar, I equal to 1 to n. So, this is I mean to say x 1 y 1 bar plus y 2 bar x2 plus your yn bar and xn. So, f of alpha, if I consider f of alpha, then f of alpha will be equal to f of sigma xi alpha I. So, this is equal to sigma xi and f of alpha I equal to 1 to n. So, if at all there is a element beta belongs to V such that f of alpha equal to inner product of alpha and beta. So, then this means that f of alpha will be equal to this one implies your sigma xi f of alpha I equal to 1 to n must be equal to sigma yi yi bar and xi I equal to 1 to n. So, comparing the coefficient of the xi I will have, so this implies that f of alpha j equal to yj bar or yj equal to f of alpha j bar. So, this implies the beta has to be of the structure of sigma f of alpha j bar and alpha j equal to 1 to n. Okay, so, this thing we have done without bothering about the geometrical interest of this problem, please. Suppose we want to know what is the geometrical interpretation of this type of concept. So, to understand that one, see here beta certainly belongs to orthogonal complement of null space of F. Let me clarify this once. What is the meaning of that one, please? So, let W denote the null space of F and W complement the orthogonal complement of W. I mean to say any element alpha belongs to W and beta belongs to W complement, they have to be orthogonal to each others. I mean to say inner product of this will be equal to 0, inner product of alpha and beta will be equal to 0. So, here I can write down the vector space V as a direct sum of W and W complement, orthogonal complement. For any element V, alpha belongs to V, alpha will be something like W1 plus W2, where W1 belongs to capital W and W2 belongs to W bar, please, orthogonal complement. Since f of alpha equal to inner product of alpha beta, this is equal to, I can write down inner product of your W1 plus W2 and beta. So, this will be equal to inner product of W2 and beta, because inner product of W1 and beta equal to 0. So, that is why it is like this thing only. So, in fact, if P denote the orthogonal projection of V on W complement, orthogonal complement of the W, then I can say f of alpha is equal to f of p alpha. So, what is p alpha? Since f is a linear functional, f is a linear functional, so dimension of the basically range space of f or W complement is 1. Let gamma be any non-zero element of W complement. So, I can say gamma will basically basis for the W complement, because the dimension of the space W complement is 1. So, certainly if I take a singleton non-zero element gamma which belongs to W complement will act as the basis. So, this implies for any element alpha belongs to V, the orthogonal projection of alpha, orthogonal projection of alpha will be the best approximations of then P alpha is the best approximation of alpha in W complement. So, this implies your P alpha will be equal to inner product of alpha gamma by norm of gamma square and gamma. So, this implies f of alpha, I can write down this is equal to f of your P alpha plus I minus P of alpha, okay, which is equal to f of P alpha, because this is equal to f of P alpha only, because I minus P operating on alpha will be in W, that is null space of F. So, that will be definitely orthogonal to gamma. So, therefore, it will be simply f of P alpha, please, f of P alpha I can say. Now, f of P alpha, so now it will be equal to inner product of alpha gamma by norm of gamma square and f of gamma. So, this implies that if I say that this is also equal to f of alpha. So, this implies if I know what is the appropriate beta, I can also calculate from this. So, f of alpha which is equal to inner product of alpha beta. So, this is equal to inner product of alpha gamma by square and f of gamma. So, this implies I will have beta equal to f of gamma divided by a square and gamma. Okay. So, this is the basically geometrical interpretation of this beta element, please. We shall now raise a questions. See, we have proved that existence of unit vector beta in V for any linear functional f, assuming that the inner product space is finite dimensional. If we take out this concept that V is finite dimensional, if I replace finite dimensional inner product space, by infinite dimensional inner product space, whether we can also have such type of relation. I mean to say, is it possible to say that for a given linear functional on that space, there will be a unique vector in the vector space, the linear functionals can be written as inner product of that fixed vector in the space? Answer is no. This will be discussed in the next class, please.